Okay, let's start. Welcome back. Any questions about frequency response of common source amplifier till now? All good? Okay, let's continue. So till now we have been dealing with the common source amplifier as decoupled or uncoupled systems between the gate and the drain, right? By uncoupled, I mean the time constants of the gate side is not affecting the time constants on the drain side and vice versa. And that's what we have been dealing with till now. And this was the structure. Right, so this was the incremental equivalent. Obviously, in this case, I have neglected the coupling capacitors at the input and the output side. Why did I neglect that? This is not the exact one, right? So you'll have to feed the input. So you had a capacitor in series with the input source. Similarly, you had a capacitor at the output also, which was connected to RL. I haven't included RL here, so let me put that back. GL. So why, I mean, is it a fair enough assumption to neglect it, or I mean, should I introduce them back? Yes, please, anyone. Is the question clear? Can you repeat the question to me? What is this to do with high gain? What was the question? We had a capacitor here, right? We had a capacitor here and we had some capacitor here. This was C1, C2. And we did a bunch of calculations in the last class. I think last 2 classes, we did a bunch of calculations. We developed some intuitions also as to what will be the time constant associated with each of these capacitors. Then suddenly I come to class today and I say that I will not use them in our analysis. So is that a fair approximation to make, or I'll incur some error? It's fair? Why? Can you? I couldn't hear you. Can you? Right. Okay. So I mean, it is expected that we'll put the values of we'll choose the values of C1 and C2 such that the signal flows through it. Right? Ideally, they should be infinitely large. If they are not, then we'll have to choose some values in order to ensure that the signal actually flows through it. And we saw what were the constraints. The poles associated with C1 and C2 should be at sufficiently lower frequencies and so on, right? Assuming that those constraints are met, then I don't have to carry forward the effects of C1 and C2 for my further analysis, right? So this is again a typical thing in design, any design. You don't put the entire thing together and find out a big solution, right? The big expression might look cool in piece of paper, but it's essentially useless if you cannot do any inference out of it, right? So essentially, what we would like to do is to remove as many irrelevant or less relevant information from our analysis as we progress, right? And you will see this will be the theme. This will be a theme for any analog circuit course or any design course that you will take, right? So making approximation is the key towards getting any intuition, making the correct approximation, obviously. And often, I mean, when I was a student, I was also told the same thing, and I'll also repeat the same thing, that making the exact analysis is the easier part, right? I'll give you the full-blown circuit, you write KVL, KCL, and you will find some expression. Provided that you don't make any algebraic mistakes, you will always get the right answer. But that's a useless thing to get because you will not have any intuition with it, right? You need to understand if I need to move some parameter to high, small, low, left, right, and so on, you need to understand which is the most dominant thing that you can change, right? So for that, you cannot make any sense if you have 9 parameters in the equation. So you'll have to cut down to as low as possible. Obviously, in the process of cutting down, you will have an error. But all you have to ensure is that you are not cutting down the dominant term. As long as the dominant term is there, you are good. And for that, you need to understand, you need to develop the intuition or with practice that which is the dominant term, right? Which is the relevant term. So that is something that you need to inculcate. And that only comes after you engage with the subject and you go through the lectures and you do the assignments. Okay, granted that we neglected we can neglect C1 and C2, and in this case also we figured out what are the time constants. What are the time? These two systems are uncoupled. Again, I am repeating myself. These two systems are uncoupled because the time constant at the input loop is independent of the time constant of the output loop, right? So whatever is happening at the output is not affecting the input. And the only way the input is affecting the output is through this guy, right? Which is frequency independent. Okay, so far so good. But however, now we have to put back one component which we have been neglecting, and we have to see whether this is something we can neglect or we have to deal with. Okay. And when we ended the last class, we were talking about the Miller effect. What was the Miller effect? A quick recap. So if you have a voltage controlled voltage source, right, of value minus A, and let's say you put a capacitor, you can put any capacitor, inductors, resistor on any contraption around it. So the impedance looking here, right? The impedance looking here seems like 1 plus A times C, because the current that you are drawing is, if you apply a test voltage V test, this voltage other side will be minus A times V test. So the current that you will be drawing is V test 1 plus A times SC. So it almost seems like for the source V test, it almost seems like it is driving a capacitor of the value of 1 plus A, right? So what is a voltage controlled voltage source? A voltage controlled voltage source is a contraption that amplifies the input available between two ports. Right? So in this case, the sign is opposite. So let me write it in this way. And it has a zero output impedance, which means that whatever I connect here, right? Whatever I connect here or between this to another terminal, the voltage at the other side of the voltage control voltage source will not change, right? So the implications of that is what is a Miller effect, right? Is the increase of capacitances. So why is a Miller effect? Why are we talking about Miller effect in our case? In our case, we are talking about Miller effect because it seems like in the absence of CGD, if CGD were not there, the voltage at this voltage at the output node, right, will be minus GM times VGS times by, let's say, GDS plus GL. If I neglect CDV, right? If I neglect CDV, this will be the voltage, and this voltage is VGS. So it seems like there is a inverse gain relationship, or rather there is a gain relationship between two terminals of the common source amplifier, the input and the output, and the other input, and they are 180 degree out of phase, right? So if that is true, then we can expect some sort of Miller effect. If we put back a capacitor between the input and the output port, right? So that is why we are talking about Miller effect. However, we saw that there is a critical difference between the traditional structures of Miller effect and the structure that we are dealing with. And what is the difference? What is the critical difference? Pardon? Right. Voltage control voltage source and voltage control current source. So when dealing with Miller effect, we are assuming that it's a voltage control voltage source, right? So putting a capacitor or any contraption for the matter doesn't change the output voltage. But in our case, it's not a voltage control voltage source. It's better modeled as a voltage control current source with some resistance attached to the output. So now if you naturally connect something to the output, you are changing the effective resistance of the output or impedance of the output, which means the voltage is changed, right? So in its truest sense, Miller effect we cannot use, right? But we will see now with more analysis if Miller effect can be used under certain circumstances. Okay, so that's what we will see now. So let's get back to business. And for this, what we have to do is we have to find out the full-blown transfer function between V naught and Vi of this contraption, right? There's no way out of it because we actually have to find out whether Miller effect is true or not, or what are the other consequences of putting a CGD across the terminals. Okay, so let's do that. So I'll club all the conductances at the output node and call this GS. This is GS, and let me call this CL. Right? I mean, since at the output side everything is a load, right? So GL and CL, and with the assumption that CL is equal to CDB plus any extra capacitance, right? Because our common source amplifier might be driving something, right? So that something might have some capacitance associated with it also. If it's driving another common source amplifier, right? So this capacitance will be what? CGS, right? If it's driving another common source amplifier, this capacitance will also be CGS, right? So obviously, when you are making an amplifier, you are making an amplifier to drive something. There's no point making an amplifier which just sits and does nothing, right? It will have to drive something, which means there will be a GL and CL associated with it also, right? So let's assume that it is driving something. If it is driving something, it will have a capacitive load. And we have to assume something to start off. We have to assume some order of the capacitances. So let's assume CL is at least of the order of CGS. Right? Whenever we have to make approximations, we need to understand which is big, which is small, and so on. So we need to understand what is the order of the capacitances. Right? So this is CGS, this is RS, and we have CGD. Okay. And like before, I mean, I would like to reduce the number of nodes for calculations. So I will Nortonize the input port. So this becomes VS GS. This becomes GS. Okay. So we'll have to now basically write out the KCLs at two nodes. Yes. Yeah, so GDS is clubbed into GL. GDS is being clubbed into GL, right? Parallel combination, so everything is clubbed in. So let me write that down also, right? So otherwise, I might also make a mistake later. So GDS. Okay. So let's write out the KCLs. So help me with the KCL equation at the first node at the input side across CGS. What should I write? Okay, so VGS. So let's VGS GS plus what is the current? So basically all the currents coming out, right? One current coming out this, one current is this. What is that current? Second current? Is CGS times VGS. What is this current? VGS minus V naught SCGD. This is equal to? This is equal to VSGS. So let me put things in a proper order. I'll club all the things together. So this becomes VGS times GS. Yes. Right? Now let's do the other side. Well, what will that equation be? What will the equation on the other side be? KCL at output node. So you'll have V naught. What will be the current associated with V naught? The obvious ones are GL plus SCL plus SCGD. And what will be the effect of VGS? Minus, so if I want VGS right here, VGS. So minus of what? SCGD. Anything else? Plus GM. Right? This is equals to, everything equals to 0, right? Okay. So 2 by 2 matrix form. So we can express in that form. Right? Just verify that I'm not making any mistake, right? Because otherwise it can be painful when the expression becomes big. Okay, so V naught over Vi. So V naught is equal to determinant of the matrix and in the numerator I'll have the determinant of, I'll replace this guy with this guy, right? And take the determinant. So this will become, fortunately we have a 0. Okay, so actually I should use the phasor notation, right? So this should be V naught, this should be Vs. So let's put the S squared terms together. So we'll have CGD CL plus CGD squared plus CGS times CL plus CGS CGD. And I'll have another SS squared term from here, right? So minus CGD squared. Okay. So this cancels. So let's simplify it to whatever extent we can. Okay, fine. Big equation. So we'll have to make sense out of it. So let's start one by one, right? So the first thing that we should check is whether the DC gain of this guy is correct, right? So what is the DC gain? In this case, S equal to 0. Yeah, so DC gain is GM over GS. So that's correct or incorrect? What do I expect DC gain to be? Yeah, right, minus GMRL. So are we getting that? Yeah, okay, good. So at least that's fine. Anything else that we can make sense of? I mean, one thing that we can obviously make sense of is if you put S tends to infinity, everything goes to 0, right? So that is that expected? If we put S tends to infinity, should everything go to 0? Should output go to 0? Right? Okay, fine. That's also good. So two things that we could easily tick off are ticked off. Now comes the interesting part. So how many poles, how many zeros do you see here? 2 poles, 1 zeros. Okay, great. So which means that I can express V0 over Vi in a generic form as some DC gain A0 1 plus S by Z by 1 plus S by P1 1 plus S by P2. Right? Again, I'm not writing P1 and P2 as minus P1 minus P2 because assumption is that if this guy is stable, then poles will be on the left half plane, right? Okay, fine. So now we'll have to understand why do we have the poles and why do we have the zeros? So since 0 is the most, seems to be the simplest, right? Looking at the expression. So let's attack that first. So what is the 0 frequency? How can frequency be equal to DC gain? Yeah, so how will you establish, looking at a transfer function, how do you establish what the 0 is? Numerator goes to 0, right? So essentially V0 should go to 0. What value of S? At what value of S? Yeah. So at what value of S? V0 goes to 0. So So in this case, other than s tends to infinity, obviously, s tends to infinity means 0 at infinity, which means s by infinity. So that's irrelevant. Okay. So is there any non-infinite value of s for which your V naught goes to 0? In this case, I can clearly see, right? If I plug in s equal to Gm by CGD, then this guy goes to 0, right? So actually, I should write it as negative because it's not necessary that all zeros have to be on the left half plane, right? So 0, so Z is equal to Gm by CGD. Okay, so this is after writing out the transfer function. But since this is a circuit design course, we'd like to have an intuition as to figure out, we need an intuition to figure out, looking at that circuit, whether we'll have a 0 or not, right? So that is the next thing that we would like to do. So let's see. So let's say we have developed some VGS. How we have developed the VGS is immaterial, but let's say we have developed the VGS so that we would like to only see whether, what is the final impact at the output. Okay, so I'll remove all this stuff and we assume that some VGS has been developed. And with the understanding that for this you require some source at the input and all, right? So the reason I am doing all these things is because when we are saying that we have a 0 at the output, what are we doing? We are setting V naught to 0, right? So from this expression, mathematically, what is the definition of 0? It is that value of S for which V naught goes to 0, right? You don't have any doubt about that, right? Okay, so if that is true, then can I flip the argument and say that in a circuit, if I set V naught to equal to 0 and try to find out the value of S, whatever value of S I will get will be the 0 frequency, right? I just flip the argument. Okay, so let's do that. So why is 0 so holy in circuits? Is because we know a lot of things can be neglected then. A lot of things go out of the picture. So let's say V naught equal to 0, which means what? This voltage is equal to 0. Correct? This voltage is 0, this voltage is 0, which means I don't have to bother about these two guys. Correct? So, fine. So all we have to do is now to figure out under what condition this is going to materialize. Okay, so let's solve. So what is the current through the CGD if one side of the CGD is 0? Pardon? Output is shorted because what we did, we flipped the argument, right? So what was the argument? Argument is at 0 frequency, V naught is 0, right? That is the definition of 0, right? So we are starting from that definition that I know that if I hit the 0 frequency, 0 value of S, not frequency, not omega. If I hit S equal to that 0 frequency, then our output will be 0, right? So that is the definition of 0, right? So if you are not comfortable with that definition, let me take a step back and try to convince you in this way. So let's say I have a transfer function H of S. Which has some zero sum poles. Okay. And I want to find out in the complex plane of sigma and j omega, right? I can write out, if I can find out the poles and the zeros separately, So let's say I have some pole here, some pole here, some 0 here, some 0 here, right? I mean, I just arbitrarily chose the positions, need not necessarily be that. So this is a value of S, right? This is some value of S, let's say SZ, which is equal to maybe some sigma Z plus J omega Z. So similarly, this is also some value of Z, which is sigma Z minus J omega Z. Okay. So what happens if I plug in S equal to SZ in this transfer function? So what is V naught of SZ? 0, right? There should not be, I mean, I hope everybody is happy with this argument. So if that is the case, what I am essentially saying is that if I have to find out the 0 from this transfer function, I will set this to 0 and back calculate. Okay, so that's what we are doing here. So we are setting the output to 0. Setting output to 0 in circuit has a lot of, I mean, it makes life very easy because we have a reference ground. If some other node also goes to 0, a lot of things can be thrown out. So that's what we did. If we set the output to 0, anything between output that output node and the ground, I can throw away. Okay. So now I have to figure out, is there a value of S for which this condition is valid? For that, I am back calculating. So is the argument clear? Okay, great. So now what is the, if this is clear, if this is what it is, if this is the case scenario, then what is the current through CGD? This is S CGD times. Why should be 0? At that side, we are setting V naught equal to 0. We are not setting VGS equal to 0, right? Because input is still there. There will be some input, right? So there is some input, and that input will create some VGS. Correct? So, I mean, instead of, again, finding out that input and finding out that VGS, and then calculating, I basically said that there will be some VGS, and let's see whether we can get some solution. Okay. So clearly, this VGS is a function of input. This is not a independent thing, right? Okay, so this current is SCGD times VGS. Satisfied with that? Okay. So now this current essentially is equal to GM times VGS. Yes. Correct. Okay. Good question. So saying this is short circuited, but will that be the correct assumption? So let me ask you the question in another way. If you find any voltage in a network to be equal to 0, does that mean that is physically shorted to ground? Did not necessarily be, right? So this is that scenario where a voltage is set to 0, but it's need not necessarily shorted to ground. Okay. Okay. So okay, fine. So why is that question important? That question is important is because if this guy is shorted, all this current will go into the short, right? So we are modifying the circuit, but we cannot modify the circuit. Circuit is whatever it is. Okay. So this current has to go into GM times VGS. So what is the KCL at the output node then? SCGD is equal to GM times VGS. So what value of S satisfies our assumption of 0? SCGD times VGS, right? So GM over CGD. So this becomes your 0 frequency, right? You don't have to write the transfer function. You can basically look at the circuit, set the output to 0, and figure out whether there is a value of, indeed a non-zero value of S, or non-zero, I shouldn't say non-zero, non-infinite value of S for which this case is satisfied. Okay. A trivial example is, A trivial example is something that we have done earlier, but not in this context. So this is V0. Right? What type of filter is this? Yes.
Made the output equal to 0, and we are assuming that it is 0 because of that S only.
Yes. So essentially, what are you doing? We are in search in that entire sigma j omega plane. We are searching for this point. No, that we cannot assume, right? We are applying a VI. So we are talking about at a particular frequency, whether it's 0 or not time. Right? This is a phasor. We are doing a phasor analysis here, isn't it? Okay. So again, I mean, if this is confusing, think in this way. So let's say you have this sigma j omega, the entire S plane. Okay. So when we are trying to find out V0 over VI, V0 S over VI S, so this is H of S, right? So what is the assumption here? If I have to find out H of S, right? So let's say experimentally I have to find out H of S. I go to the lab, I want to experimentally find out H of S. What will you do? So let's say we remove this. So let's say you have a box. You know the transfer function is something, some H of S. You will have to find out experimentally what is H of S. What will you do? You have every equipment possible in the lab. So talk me through the setup. For that, you have to find out V0 first, right? Experimentally. Okay, so what will you be using? You'll be using a voltmeter. Okay. Okay, one by one. So first you go to the lab, you set up, you plug in your device, you give proper biasing conditions, everything. Then now what is the next step? You'll take no input. No, important. You have to give an input. You have to give a sinusoidal input, not any input. Right? You have to give a sinusoidal input, right? So you give a sinusoidal input, let's say VI or VP sin omega t. And then you will observe the output, right? What will be the output? Will be something, so now what will be the output? If you say that H of S is something, so the output will be mod of H of j omega naught times VP sin omega naught t plus some phi, right? So what will be, so this is one data point, correct? This is one data point. And if you have to find out H of S, you are essentially saying that I need to fill up this entire S plane, correct? But you have found only one data point by doing one experiment. So what if you want more data points, what do you need to do?
You have to find out at what frequency each.
No, that is different thing. I mean, that is another question I'll come to. So experimentally, I need to find out what is H of j omega. Step response has an issue, is because it has. So I presume what you are saying, you give a step response, you know that the transfer function of step response is 1 over S. You find out the profile of the output, take that and get it done, right? In principle, that can be done, but there is an issue. The issue is this. So normally when you connect a wire like this, right, it is expected that the wire is a perfect short circuit. But in reality, it is not. A wire has its own inductance, own capacitance, own resistances. So essentially that wire is itself an RLC filter. Okay, so now when you apply, so basically what I'm saying is, if you have H of S, so here it's going through this. So if you apply a step here, there is no guarantee that you are getting a step here. Do you see the point? However, if you apply a sinusoid here, there is a guarantee that you are getting a sinusoid here. It might be smaller in amplitude, it might be shifted in phase, but you are going to get a sinusoid. So that is a property of an LTI system. That is why sinusoid is a special function. E to the power j omega naught t is the eigenfunction of an LTI system. This is the physical meaning of that. Right? That is the only type of input that you can give which retains its shape when it passes through an LTI system. Okay. So that's why you cannot, do this analysis using any other type of input other than a sinusoid. So effectively, if you are stuck with sinusoid, which means that you have to basically vary omega naught, right? You start from omega equal to 0 and then vary till whatever frequency you can. So essentially, you are making a table, right? You are making a table of omega naught and mod and angle, right? So you start with omega naught equal to 0, blah, 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 and you get a list. So when you get a list, what essentially do you get? You get whole bunches of mod of h and phi. From there, you can reconstruct the transfer function. Correct? Okay. So if now, what I'm now trying to get at here is that when we are trying to find out what is the value of, what is the frequency of 0, we are essentially in search for a value of s for which this guy goes to 0. Correct? However, you should note that S is sigma plus j omega. Correct? S is not only j omega, but omega is the frequency that you are varying. Right? Omega is you are varying. Physically, when you are tuning the frequency, you are varying omega. You are not varying sigma. Sigma is not in your control, which means that you might not have a 0 at a particular value of omega, but you can have a 0 at some value of s. They are not the same things. Correct? So experimentally, you will probably not be able to find out the location of the 0 because you can only vary omega. Correct? But let's say I give you some box where you can vary s, both sigma and omega. Then in principle, you can sweep for all values of sigma and omega to find out where the output exactly goes to 0. Right? So assume that we have that box, and for that I can sweep the entire S-plane. And if I have the ability to sweep both sigma and omega, after sweeping somewhere, I will come up to this point, right? I will come here. And then I will suddenly see that output is 0. Right? I am in search of that point. So one way to do is to say that I will keep on searching for the rest of my life. Other way to do is to say that I assume that that exists and I'll try to find out the corresponding value of s if it exists or not. Okay. Does that answer your question? Somebody asked me the question, right? Okay. Okay. So this is what we are essentially doing, right? We are setting the output to 0 and trying to find out if a value of s exists, not omega. If a value of s exists for which the output goes to 0, right? So okay, let me give a trivial example. Let's consider this circuit. We take the output here across the resistor. We know that this is a high-pass filter. We have done this before. But if we have to use the same methodology that we are using now, what will we do? We will essentially say that in order to find the location of a 0, in our search for 0, we will first set the output to 0. So this goes to 0. Then what is the current? The current is Vi times SC. Then what is the voltage that gets developed across this R? The voltage that gets developed is Vi times SC times R, right? If A0 exists, right? So this is only if A0 exists, and right? And if A0 exists, this V0 becomes Vi times SC times R, and we set it to 0. Then what value of S satisfies this? S equal to 0 satisfies this. So this means 0 at S equal to 0. Right? So that we already know, right? We already know from our full-blown analysis. You can find out the transfer function. You see that there is a 0 at DC, right? So if we do the other one, the low pass filter, right? If we do the low pass filter, what will we see? Again, in search of a 0, what will we do? We'll set V0 to be 0. So this becomes 0. Then what is this current? This current becomes Vi times G, right? Then what is V0? Then V0 becomes Vi times G by SC. And we set this to 0, which means a 0 exists, but 0 exists at S equal to infinity. S equal to infinity, right? So since a 0 exists at S equal to infinity, this is equivalent to saying that there is no 0. No finite 0. Okay, so let's do one more where the 0 is neither at 0 or at infinity, right? So let's do an LCR circuit. Again, same principle. If we take the V0 across this LC, note that in order to find a 0, the location of the output is important. This is unlike that of a pole, right? In a first order system, the pole is essentially the time constant, and time constant is a property of the loop. It's not a, it's independent of from where you are taking the output. So that is a critical difference that you should keep in mind, that a pole is independent of where you are applying the input, from where you are taking the output, but not 0. 0 is strongly dependent on exactly where you are applying the input and where you are applying the output, because we are searching for the condition of V output to be going to 0, right? That is very specific. So again, let's do the same thing. So this becomes 0. So this current becomes same old, right? Vi times G. So we set V0 to be 0. Now what is V0 now? This current Vi times G times SL plus 1 over SC. Correct? So if we set this to 0, what do we get? We get SS square LC plus 1 by SC is equal to 0, which means we get a 0 at S equal to plus minus J by under root LC. Right? So we get, in this case, we get 2 zeros at and the location is neither S equal to 0 or infinity, right? So the reason I wanted to show this third example is to show you that it's not only true for S equal to 0 or S equal to infinity. I mean, this way of finding out the location of the 0 is generally valid, and it should be, right? Because if you hit the value of S which corresponds to a 0, the output should go to 0. So we are essentially doing the inverse of that. We're setting the output to 0 and trying to find out the value of S. And going forward, for all systems, this is the methodology that we will use to find out the locations of zeros, right? So okay. So we have been expressing this in this form. A0 is, we know what it is. It is GM over GL 1 minus S by Z. We know what is Z now. Now we need to find out what is P1 and what is P2. Okay. So obviously, second order equation, moment we see, we would like to do quadratic. but I'll go mad, right? So if I do quadratic on this, so we'll do approximation, right? We can do certain approximation based on the assumption that the poles are nearby or poles are far apart, right? We have done it once already. So let's use that, right? Let's assume, again, there is no basis of assumption till right now because we don't know much. So we'll assume something and go back and verify whether the assumption is correct or not. Okay, so let's assume something that poles are far apart, right? So assume poles are far apart. Assume P1 is much less than P2. Okay. So if that is the case, what is P1? Tell me. So let's say AS squared plus BS plus C equal to 0 is my quadratic. It has two roots, which are poles P1 and P2. Let's assume a mod of P1 is much less than mod of P2. That is, I mean, they are separated apart. By the way, I will remove the mod after some time because that's how circuit designers talk. The negative pole doesn't exist. So we basically, when we say one pole is much smaller, we assume that the mod of the pole is much smaller, right? So if this is the case, then what is P1 in terms of ABC? C by B. Okay. Right, rather minus C by B. So we'll drop the minus after some time. Let's stick with it. So let's see what's going to happen here. So this is equivalent to GS GL by CL plus CGD I think I missed something in the file copying. This expression doesn't look full, right? GM. TGD GM, right? Okay, right? Yeah, so this is even dimensionally not correct. Okay. So the other thing that why are you doing all these things? We are doing all these things with the hope that we can replace these second order expression with bunch of first order expressions, right? Which means we are trying to figure out if we can model our circuits as simple RNCs, right? Bunches of Rs and Cs, first order RNCs. So in a first order RNC, what is the format of a pole? It's some conductance over some capacitance, right? 1 over RC, or in terms of, since we are expressing everything in terms of conductance, it's conductance over capacitance, correct? So if we have to express that, if we have to express it in that form, so clearly in the numerator, I have conductance squared, right? So I'll divide by one conductance. Let's divide by GL. Okay. So, or rather multiply by RL. So if I multiply by RL, GL goes to 1, right? So this becomes GS by CL plus CGD, GS by GL plus CGD plus CGS plus CGD, GMRL. So I club a couple of terms together. You will soon see why I am doing that. Okay, so this is P1. So let me sketch the circuit once again to make sense. Okay. So, so let's let me ask you this. Let's say if CGD were not there, right? What would have been the pole associated with the input loop? Pardon? GS upon CGS, right? So if this CGD wouldn't have been there, I would have gotten the pole to be at minus GS by CGS. Conductance is GS, capacitance CGS, right? So now this is not the case. In our case, we have this. However, the conductance associated with it is still GS, right? With that node, right? So that's good. We have GS on top. Okay. So the bottom guy, the denominator, has to be some equivalent capacitance. But in that capacitance, I should expect a CGS, right? So that fortunately is there, right? Let's concentrate on this guy, right? It's 1 plus GMRL times CGD. What do you think is that term doing here? GMRL is a gain, is a DC gain of the amplifier, right? So this effectively becomes, this is 1 plus A, let's say A naught, right? 1 plus A naught times CGD. What does this remind you of? Miller effect, right? So effectively, we are seeing some sort of Miller effect in our structure also. Okay. So even though this is not a voltage controlled voltage source, it's a voltage controlled current source, still we are getting some Miller effect. Okay. So this is, that explains that term. Why do you think this term appears? Or, I mean, okay, before I ask you why do you think this term appears, let me ask you, what do you expect A naught to be? High, low? I mean, at least you are designing an amplifier. So what do you expect an A naught to be? High, right? Okay. And typically, CGD, as it turns out, I mean, this is again information. So CGD is sometimes of the order of CGS by 10. I mean, I should write it in another way, right? So I should say CGS is typically of the order of 5 or 10x of CGD. I mean, this is again, I mean, you can change, you can skew your device in such a way that this assumption is not correct. But in general, this is a fair enough assumption to make, right? CGD is the overlap capacitance. CGS is the channel capacitance. We expect the channel capacitance to be much more than the overlap capacitance. So this is typical range of CGS and CGD. A naught you expect to be very high. So compared, what about GS and GL? Do you expect GS and GL to be of the same order? They can be, right? Generally, let's say you have an amplifier, you have a block that is being driven by another block, and this amplifier is driving another block, right? So effectively, you can say that GS and GL can be of the same order. Again, it not necessarily be the case. If it's not the case, the assumptions will change and your expressions might change. So which term do you think in the denominator is the dominant term then? 1 plus A naught times CGD seems to be the dominant term, right? Because CL, again, is of the order of CGS, right? That's what we assumed at the beginning. So GS over GL, approximately 1, or maybe slightly more than 1 or slightly less than 1, which essentially means that if A naught is high enough, that is an important assumption. If A naught is high enough, if you have made a proper amplifier, right, then your pole essentially becomes approximately minus GS by 1. Even I can drop 1 plus if A naught is high enough, right? CGD. Okay. But again, multiple assumptions built into these approximations. The assumption is A naught is much more than 1. Assumption is your CL is of the order of CGD. right? If you put a very big load suddenly and then CL becomes very high, then obviously in the denominator, the dominant terms change, right? So those things you have to take into account. And this term, the first term that is sitting here in the denominator, there is actually explanation for that. That appears, I mean, the argument for that is, since our amplifier is not a voltage control current source, we don't expect it to be a perfect Miller, we don't expect perfect Miller amplifier, right? Had our amplifier been a perfect voltage source, then this first term wouldn't have been there. I would have only had the Miller term and the CGS, right? What I'm essentially saying is this: if we had what would have been the pole associated with this node? So what is the capacitance looking in? CGD times 1 plus A, right? So this basically becomes what would have been the pole then? Minus GS by CGD plus 1 plus A times CGD, right? This if that were a perfect voltage control voltage source. In our case, it's not. Since it's not, we don't expect the same location of the pole, right? We expect it to move around a bit, and that is an error term, right? We can attribute it to that. Yes.
So couldn't we just recognize that current dependent current source into a different dependent voltage source and then apply?
Yes, we can. So okay, so why don't you tell me exactly what you are trying to get at, then I'll explain. So which one you wanted to Theveninize this?
Including this.
Including the CL, right? Yes. So if you do that, what will end up happening is, see, the main problem is this node here, this node voltage here, even in the absence of CGD, is frequency dependent, right? Because GM-VGS goes into a frequency dependent impedance, right? So this voltage here, so essentially, so if I give you this analogy, so let's say your Miller amp is A of S, right? Let's say the Miller amp is A of S, where A is it's a low pass filter. So let's say A naught by 1 plus S by P. So that is the scenario here, right? So that is the scenario here. So let's say CGT is not there, then voltage here is a low pass filter, right? GM-VGS flowing into a parallel combination of R and C. So we have a pole. So this is what is getting modeled like this. Okay, so minus, and I put a capacitance across it. Okay, so what is the impedance looking in? So let's say I put a V test. So this voltage will be minus A naught P test by 1 plus S by P. Correct? So what is the current now? I test is just 1. Correct? So what is V test over I test? Correct? So see, this is not a full capacitor, right? This guy is not a capacitor anymore. Right? Why? If P were infinity, right? If pole didn't exist, if P were infinity, then this would have been a capacitor of value C times 1 plus A. So this is another impedance, sure, but this is not a capacitor. Make sense? So let's say I have you put together something and you get an impedance which looks like, so this is 1 over, something is wrong. So I can say that this is some Z of S, where value of Z of S is this, right? So this is a frequency dependent element or a combination of elements, right? I can break it down into frequency dependent capacitance, inductance, resistance, and all. I can do that, but it doesn't give much intuition, right? So that's why, I mean, whatever in principle you were saying can be done, right? In fact, there was a very good paper few years back, a couple of years back, where they did some variations of this. They didn't include CL, but people are still publishing on Miller effect. So that's a good paper. You can take a look at it, how to Theveninize it and get another set of intuitions. But anyhow, for the purpose of developing an intuition in our case, this will probably be a decent enough assumption. Okay. Any questions? Okay. So P1 is done. Z is done. So P2. Let's see P2. So P2 is what? Minus B over A, right? So let's do that. Okay. So this again is not in the form of conductance. Dimensionally, this is not conductance over capacitance. So we'd like to do that. So what I'll do, I will club this CL in the denominator together. So this becomes CL. What did I do? So this guy, right? Okay. CGD plus CGS. Okay. So the reason I'm clubbing these two together is because, I mean, to give you a reason as to why I'm doing this. So ultimately, the output side is something goes here, connects here. This is CL. So in the absence of the CGD, the output would have been some conductance over CL. Correct? So I would like to get that CL in isolation in the denominator, because that should appear. So I am trying to club all the things that are associated with CL, and I will divide it with the terms that are multiplied with CL in order to isolate CL, right? And then make sense whether, and then try to see whether things make sense. So if we do that, in the denominator, we get CL plus right. In the numerator, what we get? We get Okay. Okay, fine. So this again, it's of the dimensionally, this is conductance over capacitance. Okay, so let's see whether this makes any sense. Again, I'm not sketching the input because poles should not depend on where you are applying the input. Okay. Okay, so let's start off with the denominator because that looks simpler. So we have a CL, this CL. So we are trying to find out the time constant associated with the second loop, right? The output side loop, right? So that is an important thing you should note. We already associated P1 with the input side. So we assume that the P2 will be associated with the output side. Okay, so again, P1 and P2, we are assuming they are uncoupled, but in strictly speaking, they will not be. But if the poles are far apart, we can assume they are uncoupled, like we did in one of the classes earlier, right? Okay, so we have CL, but we have another term here. What does that term remind you of? The capacitance, which is CGS, CGD by CGD plus CGS. It's a series of CGD and CGS. Do you see a series, I mean, looking from the output side, do you see a series combination of CGD and CGS? Anywhere? Approximately? No? So what about this guy? Right? That is, right? So if I neglect GS, then this looks like the series combination of CGD and CGS, right? So it looks like I have and that combination comes in parallel to CL, right? So the total capacitance I should expect is CL plus that series capacitance if I neglect GS. Okay, so at least that part, there is some explanation to it. So let's go to the numerator. Let's do the obvious one first. At the output node, I have GL. Is that expected? Expected, right? A GL connected to ground, so that is expected. Which term in the numerator do you think is the dominant term? You expect GM to be more than GL, less than GL, of the order of GL? Yeah, so you expect GM to be much higher than GL because ultimately the amplifier is GM over GL, right? That's the amplification factor, right? So if we are making, again, assumption we are making a decent amplifier, then GM should be much greater than GL. And GL and GS also of the same order, we assume. So the dominant term in the numerator will be the last term. Correct? So now let's see if dominant term in the numerator is the last term. Why? What is the genesis of that term, right? So we are almost out of time. So give me one more minute. So let me make the point and we'll go. So let's say I have this guy. Okay, and I apply a test voltage here. What voltage will active at this node? No, this is not VG. We are not applying anything on the output side, only applying something at the output side. We are applying a V test. What will be that voltage be? What will be VGS? Okay, so this will be CGD by CGD plus CGS times V test. So what will this current be? GM times of that, correct? So this current will be GM times of CGD by CGD plus CGS times V test. This current will flow through V test. There will be some additional current also that will be coming out, but that current will be capacitive, right? The current that will be coming through the capacitor will be capacitive. However, the real current, the resistive current will be GM times CGD by CGD plus CGS times V test. So this is effectively essentially the conductance that you see becomes at the output side becomes. So this is the conductance at the output side, right? And if you have a GL, then you get plus GL. So this is what you see here. You get one GL and you get another two, right? So essentially what I'm trying to get at here is that there is an explanation, some sort of convoluted explanation that you can associate with each of these terms. These are important because ultimately if you want to, let's say I want to move the poles P1 and P2 in different directions. Intuitively, when you are doing circuit design, you don't want to sit and write equations 2-page long, right? So you would like to have an idea of, if I change this component, pole moves this side, that side. So this will give you an explanation of the same, right? Okay, we'll stop here. I'll post an assignment today. We don't have any class on Thursday, right? So Thursday is on holiday, right? I saw that in the calendar. If not, then we'll meet. Anyway, we have a quiz on Saturday, right? Okay.